this video, we're going to talk about something called a resonance, and I have lots of cool demonstrations that we can do when we're in the classroom for this, but unfortunately I can't do them, so it might make it a bit trickier to understand, but we'll get across the main points. So when we're dealing with resonance, one of the things we can ask is it possible to shatter a glass, a wine glass or something with sound? You know, could you get an opera singer to kind of sing at a wine glass, hold a wine glass in his hand or her hand and sing at it and cause it to shatter? And two, how can we build skyscrapers that can withstand earthquakes? Now, when I write on this, sometimes this funny little line kind of happens, this one here. So please try and ignore it. I don't know how to stop it. What is resonance? Well, before we explain resonance, I just have to explain something called natural frequency. Everything that we can cause to oscillate has what's known as a natural frequency. So what I mean by that is if I had like a mass on a spring and I pull that mass down and I let it go, well, that mass would bob up and down, but it would bob up and down at a certain rate, at a certain frequency. And what you'd find is if you let this go and you let it bob up and down and you timed how many times it went up and down in a minute, say, and you found out that it went 20 times, up and down 20 times in a minute. And then you stopped it, you let it settle, and you did the same thing again, you'd get the same answer. You'd get 20, you'd get 20, and no matter how many times you do it, you'd get 20. Because this certain setup has a natural frequency of, bobbing up and down 3 times a second. Or once every 3 seconds, isn't it? Sorry. Now, if you change it, if you added another mass onto it, that number would change. But for its current mass, its current, and this current spring, that would be its natural frequency. So the natural frequency of an object is the frequency that a system, and that's the word we use to describe it, a system will oscillate, and remember oscillate is just another word for vibrate, once it has been set in motion. In other words, given some energy and left alone. It depends on the mass, shape, center of mass, and the material that is made from. But a spring isn't the only example. Another example would be a tuning fork. You know, we have the set of all the different tuning forks in the class, and when we hit each one of them off the table, they all vibrate at a different frequency because they all give off a different pitched sound. Now, why do they give off a different frequency? Well, if you look at them closely, you'll see that they're all different sizes. So they have a different shape, they have a different mass, and that causes them to have a different natural frequency. But one, the tuning fork, which has 20 hertz written on its base, because they all have the number written there, every time you hit it off the table and let it go, it will always vibrate at 20 hertz. Wine glasses as well. If you have a wine glass at home, put a little bit of water in it and just flick the side of it with your finger and it'll give off a sound. But you'll notice that that sound will always be the same. Then put more water in it and flick the side of the glass with your finger. And you'll find that the sound is different because you're changing the mass and so on, the center of mass. So therefore you're changing its natural frequency. Skyscrapers, we don't really see it, but actually they vibrate back and forth on windy days. They actually move to the left and right with a natural frequency. Person on a swing, they'd have a natural frequency. And actually our footsteps, we tend to walk, and we all have a different natural frequency, but we tend to walk with the same frequency. We have our own pace of walking. So to explain resonance then, let's say something has its own natural frequency. So let's say a wine glass has this natural frequency, okay? You hit it, it starts to vibrate and produce a sound, and this is the frequency of the sound. Now, let's say you put something beside that, like a loudspeaker, and this is hard to demonstrate, but we can demonstrate it in the class. Here's my brilliant drawing of a loudspeaker. So this is a loudspeaker, wine glass is sitting on top of it. And let's say you played music through that loudspeaker. So in other words, you sent this frequency sound going through the wine glass. What obviously that's going to do is it's going to cause the wine glass to keep vibrating. So it's not the same as just flicking it once and letting it vibrate at its natural frequency. What you're doing is you're constantly applying a frequency, you're constantly applying energy to it. The frequency that you're constantly applying, we call the driving frequency. Now, it's hard to see in this picture, but the frequency of these two are not the same. And you can see that the wavelength of the second, the driving frequency, is a lot longer than the wavelength of the natural frequency. And if you set this up and you did this in the lab, you'd get something like this. What would happen is the wine glass would start vibrating all over the place, but there'd be no pattern to its vibrations. Its resultant frequency, or the frequency of this added to this, would be very, very random. The wine glass would just keep vibrating. Sometimes it would vibrate with big amplitudes, and sometimes it would vibrate with small amplitudes. Now, where resonance comes in is if we do the same setup again. We have our speaker, I don't know why that line is there, we put our wine glass on it. But what if we set the driving frequency, the sound that the loudspeaker is producing, causing the wine glass to vibrate, what if we set that to be the same as the natural frequency of the wine glass? Well, what happens then is we don't get this irregular pattern. We get what's known as resonance. And basically resonance is where the wine glass will start to vibrate with very, very big amplitudes, very, very big amplitudes, because both of these waves are adding together, and the driving frequency is causing the wine glass to vibrate with higher and higher amplitudes all the time. Now, if we actually set this up right, we could actually cause this wine glass to shatter. And I'm going to send you a video clip which shows that as well. But that's basically what resonance is. So my definition of resonance is resonance occurs when the driving frequency is the same as the natural frequency. The amplitude of the oscillations are largest during resonance, so we can get the wine glass to vibrate with the largest possible amplitude, and the greatest amount of energy is absorbed from the driver. Now, although this is my definition, I want you to use the definition on page 194 of your book, which is slightly different, but I don't think it explains it as well, because that's the definition they tend to accept in the exam. So we don't need to worry about that graph for the moment. So I'm going to send you two videos. One of them is of the wine glass actually shattering, so it's a really good video. Have a look at that. And the other one is of a famous bridge called Tacoma Narrows. Now, this is a really old video. It's from like the 1960s or something like that. But basically, Tacoma Narrows was a bridge. And the bridge had a natural frequency, in that if you were a giant and you flicked that bridge, it would vibrate back and forth with its natural frequency. And the theory goes that this brand new bridge that was built, the wind started blowing, and the frequency of the wind was causing the bridge to vibrate back and forth. But the wind was blowing in such a way that it actually causes the bridge to resonate. And remember what resonate means. It means that its vibrations, the amplitude of its vibrations, become very, very large. And you'll see in the video, the whole bridge basically starts to kind of wobble, and the wobbles get bigger and bigger and bigger. And the bridge actually collapsed, and it was a brand new bridge, and obviously cost a lot of money. Now, luckily, nobody was injured, nobody died in it, but you can see people had to leave their cars and run off the bridge and just watch their cars basically fall into the valley below. And luckily it was a catastrophe, but nobody actually died. But engineers learned a lot from this, and they learned that bridges have a natural frequency as well, and so do skyscrapers. So when we build them, we need to put in things that will make sure that the wind or people walking across them or driving across them won't actually cause them to collapse. And soldiers, when soldiers are marching in file, when they're crossing a bridge, they're actually ordered to not march in step. So you know the way they all walk at the same speed, feet always hit the ground at the same time? They're told to break that when they're crossing a bridge, because they can actually cause the bridge to collapse if they cause it to resonate. And even the Millennium Bridge in London, which was built in 2000, I presume, they actually had to shut that down for a few weeks, because as people were walking across it, they noticed that the bridge was about to collapse. So that's all I'm going to do in this video. I'd like you to make some notes, watch those videos, and then tomorrow I'm going to talk about Barton's pendulum. And once we've done that, we have actually finished waves more or less. I'm going to give you a couple of lessons to revise. I'll give you a couple of questions, and we might do a little test maybe at the end of this week or next week.